Let's get started.
This meeting is being recorded.
Great, thank you. Okay, so we will get started. We're really grateful to have everybody here, but especially our speaker, Tomas. I'll let him describe more about himself. But I've known Tomas for several years now, and in different ways, because you're also on the geospatial group, right?
Not on the well, at some point I was, yeah. At some point I was, yeah.
Yeah, we kind of interacted with that group. Anyway, Tomas has been part of the interagency R users group from the beginning. So I've really valued his friendship and ideas, and so I think you'll hopefully get something interesting out of today's talk. And so I'm really grateful for him coming here and being with us today. And he's going to give us some information about doing text analysis in R. And Tomas, I'm going to give the podium to you and just let you introduce yourself and jump into your talk.
Okay, how do I do the present? Oh, share screen.
Yeah.
Okay.
And
so
hopefully it comes through. I don't know, Donna, do we have to set up permissions for? Oh yeah, it's coming through. Perfect.
Okay, so do you guys see my screen, right?
I do.
Okay. I'm gonna give you just out of curiosity, how many of you are statisticians here? Can I get? I don't see the hands up, but is there like a? So there's a couple of you. If you are like a real statistician, you probably won't learn much from this. This is something that I do for a mostly lay audience, just to get them introduced to the workflow in R. So I'm going to use a principal component analysis and hierarchical clustering to sort of as the analytic part of the text mining pipeline. So and I'm also doing this for students at Georgetown at the master's program in biotech. So it's kind of like a mashup of so let me, before I get into the text mining part, for those of you that are not familiar with hierarchical clustering and principal component analysis, let me just give you a very brief sort of an overview of what it is. So let me see. So principal component analysis is a way of some people call it dimensionality reduction method, which it really isn't. I mean, you can use it to reduce dimensions, but it's really just a way of looking at multidimensional data sets and sort of leveraging some of the matrix algebra to give you a view of a complex data set that you can perceive as a human, that is limited to a three-dimensional experience. So in order to do it, you have to conceptualize. If you have a data set that has observations and variables, right? So you have to conceptualize that data set as a set of points in multidimensional space, where the variables are the coordinates and the observations are the points. So the points are floating in the space, and that space is defined by the coordinates. So there's a very specific point in space where that observation sits, and it's unique to that observation. And I'm gonna skip you have to also later in the principal component analysis conceptualize the same data set as a space transformation matrix, that will allow you to use matrix algebra and finding eigenvectors and eigenvalues to really to rotate that coordinate system in the direction of the largest variance, which is the principle of PCA. And so just to give you a very sort of a very rudimentary and in a way incorrect view, but to sort of demonstrate the point, when you have these, I'm reducing this multidimensional space into a plane with two variables, right? So we have these two variables, and they define a set of points. And just for the demonstration, you can see that there's two groups of points. There are red and blue points. And if you project those points on any of the variables, you will not get a very exciting picture. That there's going to be a sort of a mixture of red and blue points. And when you do it on the second variable, that may well, similar. You can analyze the two variables independently, and you will not get a lot of information out of there. But now, what you can do, and what PCA in effect does, you can rotate the coordinate system, and instead of variables, you create components that are a combination of variables. So in this case, the component 1 is a combination of variable 1 and 2, right? Approximately 50-50 combination of variable 1 and 2. And that now, if you take that as your axis, and you have the same set of points, but now when you project that set of points on the components, you get a much better distinction between the red and blue points, as opposed to the variable. This was the variable, right? And this is the component. So I'm not sure if I should skip this. Well, no. Let me just go very briefly through this. So we start with our observations and variables, and in the text mining example, the observations are going to be documents, and the variables are going to be the words or the terms that those documents contain. And inside here, there's going to be 0 or 1, or how many times that word is present in that particular document. That's going to be our data set. So in the first step in PCA, this data set is transformed into either a covariance matrix or a distance matrix. And you can see that now we don't have variables here. We have observations on both axes, and the cells are filled with the distances between the points. So when you have a set of points, each of the points, you can measure a distance from all the other points, right? So that's the distance matrix here. And it works with covariance as well. Numerically, it's going to be, the numbers are going to be different, but the eigenvectors are going to be that you find in there are going to have the same direction with relation to the data set. And so after finding eigenvectors in this matrix, in this distance matrix or covariance matrix, you will get two outputs. One is going to be the observations, the documents that you have, and now the components instead of variables. See, here you had variables, but now it's going to be components. So this is going to be your rotated coordinate system, the same data set, but now in a rotated coordinate system. Now instead of variables, we have components. And then you will get component quotients. There's several different ways of naming this. I'm using component quotients, but component scores and component quotients. If you study these, the different people use different sort of nomenclature for this. So the second table is going to have the new components and how much each of the variables contributes to that component. And this is going to be important for us for topic modeling, because we will create these new axes that will mean something to us in the way the text documents split. And then we can examine which variables, or in this case, which words contribute to that component that gives us a good resolution in terms of splitting the documents into groups. So that is sort of the skinny of the principal component analysis. Just to give you an example, this is from something that I published a long time ago. It doesn't, what I'm trying to demonstrate here, that the dimensionality, it doesn't really matter. This is a genome, a whole genome association study with 500,000 variants. So there's 500,000 dimensions in this. And PCA basically reduces the variance in the 500,000 dimensions to two components that describe the ethnic composition of the cohort. You can see that I didn't tell PCA that there's Caucasians and African Americans in this, but based on the genetics, it groups the African Americans here and Caucasians here, without, like, with some mistakes, but that's, you know, that's the noise in the data. Yeah, so that's about the principal component analysis. Let me give you a very brief rundown on the hierarchical clustering and how that works. Let me see where it is. Maybe I can pause here. And do you guys have any questions? Is this too trivial for you, or is there anything?
Actually, I mean, folks, feel free to unmute yourself and ask a question. But no, I mean, I'm familiar with PCA, and I learned something new. So
Okay.
So you can always learn.
Okay, so let me just run through this, and if I hope this is not too trivial, but at least for some people, maybe this is going to be useful, and then I'm gonna give you the example in R. So in the hierarchical clustering, again, we are imagining the data set as a set of points in a multidimensional space. And so here's the set of points, and I numbered them here just so that we know who is who. And basically what in hierarchical clustering, we again create the distance matrix. We measure the distance of everything versus everything. And remember, I'm reducing this to 2 dimensions, but it doesn't really matter. There can be 500,000 dimensions, so 500,000 axes, and you can still measure a distance between points, and it's still going to be a scalar, right? So just so that do you understand that the 2-dimensional view doesn't improve with hierarchical clustering, but if you have 4, 5, 6 dimensions, you cannot see them like this, and the hierarchical clustering is going to help you. So we're going to create this map of distances. Now we have distances between everything and everything, and what hierarchical clustering does on the very basic level is we will take the shortest distance, which in this case it's distance between 7, 9, and we put 7 and 9 in what's called a clade. This is now our basic clade. And then we go and look what's the next shortest distance. Oops, sorry. And it's the distance between 8 and 9, but 9 is already in a clade, so this becomes a distance of 8 from the 7, 9 clade, right? And this is how we go through all the data set until we have all the points connected, right? So at the end, we end up with a cladogram that represents this data set. All right. And so again, if these 2 variables were words, present or absent in a document, and these were documents, the observations were documents, then this would be a dendrogram of the documents based on the presence of these two words. So those are the two analytical tools that I'm going to use in this. Okay. Let me switch to my R console. So I have okay. Any questions with regards to the analysis?
So I have a question. So you were using a little different terminology than what I'm used to with the hierarchical clustering. And so I'm used to it being called a dendrogram, and then each one of the groups is like a cluster, but you used a different word.
A clade. Some people use clade. I think it's from taxonomy. These are called clades.
And it's spelled C-L-A-D?
C-L-A-D-E.
Oh, okay.
And this is called cladogram, but it could be a dendrogram. Yeah. In genetics, these are pedigrees, right? It's kind of the same thing.
Yeah, it's really interesting because this is, I think, an illustration of how sort of a similar or the same sort of mathematical / statistical method, approach, whatever, is kind of discovered or named in different areas or disciplines.
Yeah, absolutely.
Yeah, and it's the same thing with principal component analysis that you gosh, I think it's in the engineering or maybe even, Richard, you might in the sort of more of the time series area where it's called has different names. So
yeah, may well be. So let me show you, just for demonstration, let me show you the data set that I'm using. And this is just for fun. I created, unfortunately, I can't show you any of the FDA data, but you can sort of imagine how this could be useful for certain things. Oops. Let me see. So I have a set of documents here that I'm interested in clustering. These are raw text documents that contain State of the Union addresses of George W. Bush, Obama. They are termed B, O, and T, and Trump. And these are just really raw text documents with nothing. I just downloaded it from the Library of Congress. There is nothing. There's no metadata. Nothing else. So I'm going to use a library called TM, which is one of the this was one of the first text mining libraries for R that was written by a PhD student in Vienna. When I started working with this about 15 years ago, so I downloaded it, and this tells you the sort of the culture of R. I started working with it, and I didn't know a lot about text mining, so I just emailed him, and he emailed me back like within 5 minutes, and we had a conversation. So you get like that access that you get to the developers. It will probably not be the same now because I don't know where he is, but anyway. So this is my R console, and I'm gonna it was the library was published. Yeah. So let me just load the library, and now I'm gonna create. So the first step in text mining, you have to prep the text, right? So you have to get it into a shape that that looks more like data, looks less like text and more like data. So I'm going to create what's called a corpus, this is just a corpus where I direct it to my current directory, which is that place that I showed you that has all these State of the Union addresses, right? So I'm going to create that corpus. All right. And now it shows up here. It has 19 elements. Those are the 19 speeches. I'm going to prepare the text. There's a couple of things, and you can go into the TM package and look up how things are done. I'm going to remove certain remove spaces, and I'm going to remove the word applause because it was messing up my analysis. It was so often that it would show up in word clouds and everything. So I just built in here to remove it. So now I have a text corpus that is already modified, right? And all the modifications in the text corpus through TM map text corpus are done on the whole corpus. So on all of the documents that are in the corpus. All right. Then the next thing is removing stop words. There are stop words are words that don't have that have grammatical meaning, but not necessarily a lot of information value, like the, in, on, all those grammatical words. Sometimes that of course decreases the information value of your document, and then sometimes if you do more advanced things like sentiment analysis or a little more of the actual natural language processing, sometimes you may not want to remove stop words. I'm only counting nouns. So maximize the editor window. Let me see. It's probably not going to be very. Yeah, I don't know how to do this so that the actual font is going to get bigger. So I'm going to remove the stop words. Oops. Control ++. No, it doesn't work. It doesn't work for me. All right. Now, the next useful thing sometimes is stemming, but it can be problematic. Stemming, it removes grammar from the actual words. So if you have I don't know, addition, additional, it's gonna make it into one word, so that you count only the root of the word. Sometimes that can mess things up. So let me see, zoom. Is it getting better? Yeah, it's getting better. All right. Okay, so I'm not gonna stem because it messes certain things up, but I'm gonna remove all punctuation and remove all numbers. And these are all commands that you can look up in the TM package. And now we can look at the corpus, and just so that you see. So this is what we have now. This is how the text changed, right? It's just nouns basically, and there's a bunch of weird stuff that's going to get filtered away, but basically it's all the documents have been transformed like this. Okay, and so now we are ready for the next step to actually create data out of this text. And what we're going to do is we're going to create a document, what's called a document term matrix, which is going to have documents as observations. Okay, and it's going to have the columns are going to be the variables, which are going to be all the words that are contained in the whole corpus. And I'm going to limit just for and this is really arbitrary, I'm going to limit the length of the words to 4 letters to whatever the maximum length of a word is. Okay, and you can do this, you can do whatever. If you feel like 4 is too low, you can use 5 or whatever. That's completely up to you. You can examine the corpus and see what your term list is and do it based on that. So now I'm going to generate the document term matrix, which is already, that's a data matrix. So we have transformed that text into data now. All right. Okay, so now I have the document term matrix, and it's here. Right, it has 19 rows and it has 7,500 columns, which are the 7,500 words that are contained in there. And then it has values for each of the observation. It tells you how many times is that word present in that document. So that is our document term matrix. Okay, now I used, for this particular exercise, I used all words that are larger than 4 characters, but you can have, if you know what you're looking for, you can have a custom dictionary. So if I just created a custom dictionary here: job, spending, America, food, border, military, immigration, right? You could create a document terms matrix that would have all your documents, but the only variables would be these, and it would give you the numbers for each of these words. All right, now I'm going to use the whole thing just for the exercise. And since we already have the text in a data format in a document term matrix, now I can apply my hierarchical clustering, right? So I'm going to use the library cluster, and I'm going to create that distance matrix that I talked about. Yes, I can filter out the ends. It doesn't interfere with this particular analysis, but I can filter out that text is still pretty dirty. It can be cleaner. So let me load that library, and I'm going to create that distance matrix from the document term matrix and run the hierarchical clustering. The way I explained by looking at the distances and damn it, I have to For some reason, did it freeze? Can you guys hear me?
Yep, I can hear you.
I'm afraid my console froze. Yeah, my console froze. Let me restart my R. Hold on 1 second. Apologize.
No worries. That's the fun of doing a live demo, right?
Yeah. That's always something, right? And I have a pre-cooked. I have slides that I can use. So let me just do this again. Let me prepare the corpus. Oops. What did I do?
I think you may need to load.
Oh, I need to load the package. I'm sorry. This is it's such a pain. We have one drive and it just messes things up all the time.
Yeah, it also slows things down, doesn't it?
Yeah, it's a pain. I don't have the packages loaded, sorry. So I have the corpus and so I'm going to do everything except for stemming, and then remove punctuation, remove numbers, generate the document term matrix, and let's see if we can run the clustering. All right, so here's the dendrogram now, right? And you see that there's three clades, three main clades. And if you look at the names of the documents, so the documents that start with T are the Trump speeches, B are Bush speeches, and O are Obama speeches. And it basically clusters all the Obama speeches together, all the Bush speeches together, all the Trump speeches together, right? So we have 7,500 dimensions in these 19 documents. And hierarchical clustering helps us basically to reduce those 7,500 dimensions into these three clades. And then we can go, if you didn't know, you could build a classifier. Let's say you have a speech that you are not sure whether it's Bush's or Obama's or Trump's. So you could do a nearest neighbor on this clade and find out that this speech belongs into the Bush cluster, right? That's so just to give you examples from FDA, we analyze, we have a lot of consumer complaints, for example. We analyze public comments from public meetings. We have a flow of documents that comes to us, which are the product applications. And for all of these, this is kind of a useful tool for the initial sorting and just to know like what are the groups and what are the terms. So let me now switch. Are there any questions with regards to this part? I can see, let me see the chat. Can I see the chat? Yeah.
So just to make sure that I understood, so you didn't do any dimensionality. You didn't do any principal components yet, right?
No. This is two independent ways of looking at the data. And this is the hierarchical clustering, just to see what is the structure in the data. If I didn't know that these were three different presidents, this would tell me something, that there are these three clades, I guess, and I could go and analyze why are there three clades.
That's pretty interesting.
Yeah. So now I can take the same document term matrix and try to do principal component analysis on the same matrix, right? We have the observations, which are the documents, and we have the variables, which are the words, right? 7,500 dimensions. Now, how do we create that new set of variables that are going to be the components that are going to give us the cut through the largest variance? If you imagine that this 19 points as a cloud of points in the 7,500 dimensional space, that cloud of points has a shape, right? So we want to cut through that shape in the direction of the largest variance, because that is where, if there are any groups in the data sets, if there's any structure in the data set, it's most likely to show where there is variance. If you have a direction that doesn't have any variance, it's unlikely to have a meaningful a group structure. So I'm going to use a library called Factominer. And Factominer has a bunch of analyses, and one of them is PCA. So I call principal component analysis on the document term matrix that I created. And I'm going to look at the two main components, two components that capture most of the variance in the 750 dimensional data set, right? And so this is obviously, there's too many variables for this to be meaningful. These are all the words, and it tells you what direction those words, what direction those variables point in these new dimensions, new dimension 1 and new dimension 2. If you have fewer variables, this is useful, but for this it's not. But the important part is here. This shows you the value of the new component. The dimension here is a component. Again, the nomenclature is not unified. So I have dimension 1 and dimension 2. That's component 1, component 2. And you can see that here you have a cluster of Obama speeches here. You have a cluster of Bush speeches, and then you have the Trump speeches sort of here in a separate quartile, right? So that's pretty neat. That means that the PCA has found a direction that separates. You can say the dimension 1 can be used to separate Republican speeches from Democratic speeches, right? You could make that hypothesis. And then the dimension 2 separates Trump speeches from everything else. You can put a threshold here on the dimension 2, and over that threshold it's Trump speeches, and under that threshold is everything else. So if you remember, the PCA gives you this sort of three different views. Let me see if I can find it now. Two different views of the data. One is observations and the components. So that's what I'm plotting. I'm basically plotting component 1 and 2 and all the observations. But it also gives you component 1 and 2 and how many, what is the contribution to the original variables to the components. And in this context, the variables are words. So basically that is a rudimentary topic modeling. You can tell if you have these two axes, and you can ask, what are the words that define this axis that separates the Republican and Democratic speeches, right? And those would be the topics in topic modeling language. Those would be the topics that define if there's if this is a speech from a Democratic president or Republican. And you can do the same for the dimension 2. So there is a let me see. You can basically get those eigenvalues and get those eigenvectors out of these. They are there in the object, in the PCA. So I can capture the summary of that analysis. And here I have it, right? So I have now, this is the first table, and this is not formatted very well. It would take a little bit of work to get it in the right format and put it in some kind of a spreadsheet. But here you have the observations, right? All 19, and you have values here. If you look at this, is the distance and dimension 1. So this here is the value, is the new value of the dimension 1 for that's your new variable for all the observations. And you have dimension 1, dimension 2, dimension 3. You can plot as many dimensions as you want. Here I'm just choosing 3. Okay. And then this is the other table where you have your variables, which are the words, right? Ability, able, Abraham, abuses, accelerating. They are alphabetical here. And here you have the contribution of that variable to dimension 1. This number here. So this is the contribution of the word ability to dimension 1. And then you have a contribution of the same word to dimension 2. So you can sort these by their contribution to dimension 1 and 2, and basically those are the topics that distinguish. And I have a canned slide here that I can show you. Those are the topics that distinguish those two axes. This is upside down because I ran it with slightly different parameters, but basically it's the same grouping. You have the Obama speeches, Bush speeches, and Trump speeches, and then you can define from this analysis, you can define the Democratic words, the Republican words, if you are looking at the party axis, which would be in this case, it would be dimension 1. Yeah, it's always dimension 1, right? So the dimension 1 is defined by these words. The Democratic side of the dimension is defined by these words. I just took top 25, and that's arbitrary. And then if you are interested in the Trump axis, which is the dimension 2, you can also look at, low Trump words and high Trump words. And that's your topic modeling. So that's all I have as an example. I just want to say that I'm using the package TM just for convenience. There's a couple of text mining, much better text mining packages now. Tidyverse is one of them, where you can do a lot more. This is not really so much natural language processing what I do. It's just I'm just getting the text data into getting text into a data form, and then I'm using statistical methods to analyze a matrix. You know, that at that point it doesn't matter whether it's text or anything else. I start thinking about the you know, variables and observations at some point. So that's all I have. If you have any questions or suggestions, I'm more than happy to entertain.
Thank you, Tomas. That was very interesting. Wow, I actually learned some new things.
Well,
So thank
congratulations.
you. Yeah, that was really good. I have one. So George asked me if you could make the code available. So
Yes, I can make the code available. It's not super exciting, really. Like, you know, like this is the code for PCA.
well, but
I can certainly, I can put something together because there's a lot of other stuff here that I'm kind of just, I'm using this for education. So, you know, there's word clouds. I can send you the whole thing. Like, I have no problem sending you the whole thing and you figure out what you want out of there.
yeah, actually, I think that's good because I think, you know, kind of knowing how to do word clouds or some of the other things you have in there, like playing with stemming, I think is interesting and helpful, and then people can just.
Yeah, I can certainly, I can send this and you guys pick what you want from there.
It's a really good presentation of the principal components approach, and I haven't really connected this with topic modeling before.
Oh,
somehow,
thank you.
I somehow missed that step earlier, so this is really helpful, actually. And I think a lot of us are having projects and increasingly some sort of text mining. And for me, we've got a variety of projects that we just need to get off the ground, really, whatever that looks like. So all technique.
Yeah, no, thank you. I appreciate. It's been super useful in, like, certain kinds of text are are easier to analyze this way. Especially with you know, science text tends to be easier because it's more idiosyncratic. Things like consumer complaints are, the language is so, like, it's just regular human language. So sometimes you don't really get that distinction, and you have to go deeper into maybe like sentiment analysis and like real natural language processing. Rather, this is, you know, there's a distinction between text mining and natural language processing. Because here I'm basically removing most of what considered language, and I'm just using the text. Yeah.
I find examples on, you know, the TM package and Corpus and things like that helpful, and even simple things like it wasn't until recently I realized the difference between document term matrix and term document matrix is it's simply an inverse. You know,
absolutely, and
so many basic things, and it's exciting.
You can use you can just the computer doesn't know that the only reason the computer knows that the documents are observations and the words are the variables is because of the orientation of the matrix. You can flip the matrix and you can do this kind of clustering on the terms. So you can look at what terms are more likely to occur together in one document.
Yeah.
And it's the same with the hierarchical clustering. You can just transform the document term matrix, just transpose it and run exactly the same code. You know, it depends on what question do you have in mind.
Yeah. Just another random thought is I'm sensing an increase in surveys via things like SurveyMonkey coming out, just because many government agencies can easily do it. And I just hadn't even thought to looking at this, some of the more.
Absolutely.
So
absolutely.
To me, this is very exciting just because I'm so new to it.
All right. Well, thank you. I'm glad it was useful.
Yeah, one thing that it's in the examples applications I've kind of worked on in the past, it's never been such a clear cut. I mean, now it's a smaller data set, and I don't know if that really matters, but it does seem like you have a really clear cut clusters. When I go back to look at the groups, it's hard to characterize them. And so here there's this clear, sort of separation, interpretation of what you have. So that's really,
yeah, I mean, it takes, there's so many moving parts, like there's a way of cleaning up your matrix by removing sparse terms that sometimes will cloud cloud the analysis. But sometimes those sparse terms are exactly what makes the distinction clear. There's so many ways of doing this. You can limit the most common words. Sometimes the most common words give you the most noise. They give you the least separation and the most noise. But sometimes those common words are exactly those that you want in your dictionary. So there's so many moving parts that it takes a little bit of tweaking to get to a point where you have a distinction like this. This was not like the first time I tried.
Yeah, that's a really good point, and I think you've done something that I've encountered and done too in the past, which is, I call them domain stop words, which when you talked about removing the word applause, so that normally would not be what would be in a stop word list, right? Because
yes,
you would think that would be informative.
yes,
but in this case, it's not, because it occurs so much. Now, some people use like the TF-IDF weighting to account for that, but I still find it's better just to remove.
I mean, the good sort of aspect of both principal component analysis and hierarchical clustering is that things that don't give you axes that don't give you separation between the documents don't matter. So you can add the applause was removed mostly because of word clouds, because it was clogging up my word clouds. Every word cloud, the biggest word was applause. But for the principal component analysis and hierarchical clustering, it wouldn't actually matter. You can even like not remove stop words and still get a pretty good distinction, pretty good separation like this. It just becomes computationally more intensive because instead of 750 dimensions, you have maybe like, I don't know, like 10,000 or whatnot. But so those are all the moving parts that you have to sort of keep in mind when you work through this.
This is very interesting, Tomas. Thank you. Any other questions for our speaker?
I have a question. This is Kyle Murray. So you mentioned earlier trying to make sense of public comments, which I can imagine are very messy. Do you have any suggestions for working with that specifically?
No, you have to, well, so even with public comments, public comments will still have some kind of domain language, right? Depending on, and we've been going through this. Do we have anyone from FDA on the call, by the way? No,
Not that I can see.
yeah, so we were kind of like, we're struggling with this a little bit because for example, for sentiment analysis, there are there are dictionaries for sentiment analysis, right? There are sort of pre-made. There's a Harvard dictionary. There's a couple of them that you can use. Whether that sentiment, the sentiment that was used for those dictionaries is the same kind of sentiment that you would see in public comments, that's questionable, right? So it's very likely that you may need to develop your own sentiment dictionary for particular public comments, for particular domain of public comments. In terms of, but it just for clustering, it actually may work, you know. It's just something that we are fooling around with, that there's nothing implemented yet.
Yeah, I imagine, Tomas, you might have similar issues as we have with kind of clustering or analyzing or mining the interviewer notes.
Mm-hmm.
So if you have a, interviewer, they're trying to do a survey and they, might record something in the survey instrument, as you could imagine, there maybe is not a lot of room for them to type things in, or they don't want to take the time.
Yeah, I mean, sometimes just the size of the text is going to, the size of the text is a quality. And sometimes if you have nothing else to cluster with, you will cluster large documents and small documents, which may not be useful. There's a way of creating the document term matrices, and that sometimes helps. You can have a document term matrix that contains the number, the frequency of the word in a document. That's the data in the matrix. So if a word appears 10 times in one document, then the value of that variable for that document is going to be 10. But you can also create, and I keep confusing this. I think it's called identification. It's not called identity. Identity matrix is mathematically something else, but it's basically a matrix where it's a binary matrix where if the word is present in the document, then it's 1, and if it's absent, it's 0. And you can create a document term matrix like that. And for certain things, that's better, because then when you have large text or small text, you will not have the differences in the frequency of the word. So it's just like, there's so many considerations. You really have to create the corpus and examine it first. Yeah,
that's actually the way I try both ways, but I like the binary encoding when there's what I call a restricted domain of discourse, meaning that which I think you've kind of referred to with the like scientific publications or something. So whereas if you're analyzing news stories that are on a bunch of different topics, then that's it's a little more difficult. But there are different weighting schemes out there that have been developed. But I typically like to try both, just what you said, the 0, 1, or the raw frequencies.
Yeah, and it will give you a different view of your data set. It may be useful. Each of them may be useful for certain things. So there's more. It's not you can't treat it as a black box that you just put it in and it's going to come out. You have to put some thinking into it, and you have to have some hypotheses in mind. You have to understand what you're looking for. It won't tell you what you're looking for.
Yeah, and you mentioned too, you brought up a good point too, that there's an art to it when you have to try different things. Yeah.
Always. Yeah.
And you can't just take one, model or whatever it is that you're doing in one area or one application or one corpus, then plop it into something else. It doesn't often work.
All right.
Well, great, fantastic. Thank you so much, everybody. And we don't have anybody scheduled yet for March, but we have some ideas of talks in mind. I just need to connect with the folks and see if I could rope them into it. And Richard, I'm going to follow up with you because that sounds really interesting. So.
Well, I think it amplifies your point that you get the generic textual stuff. As I say, I'm sorry I had to miss 20 minutes there. But, you know, Tomas, sort of you were saying, you have to think, you know, what kind of text you do, and you just can't sort of cut and paste from somebody's work into your own work. If you look at the chat, you can see we have a problem. And it's not a problem that we have documents in either of the languages. They actually get blended.
Yeah. Well,
Yeah,
for some, you know, for some of the stuff, you don't really care what the language is, because the word becomes a string of characters. It's removed from the language, right? Now, if you have redundancy, that's a problem. If you have the same word in the two languages, so then you have to figure out how to manipulate the corpus so that there's one word for one thing. But very often you have that problem even in if you don't have more than one language. In one language, you have the same thing can be described in many different ways, and you have to know that that's what you're looking for, and you have to manipulate the corpus before the analysis. So that's like the thinking that you have to do before you actually get to the data analysis. Yeah.
Sounds like normal research. You do the research, find out what the problems are, fix things. Yeah. We're all used to that.
Well, that's what makes it fun.
Yes.
Right. It must be involved. You must be emotionally involved in the thing. Otherwise, it's gonna be difficult.
Yeah, that's why I was very irritated that Mania actually left the organization, and I just thought, don't do that. You've all been in bureaucracies, you know what it's like.
Oh, yes. All right, everybody. Well, thank you so much. Thanks, Tomas.
Thank you.
Yep. And all right, well, keep an eye out for the next, for announcement, and we'll get something scheduled for March, hopefully in our usual time slot and, day and time. So, all right, well, thanks, everybody. Thanks again.
Thank you.
Thank you.